This is Physics 102A homework, Chapter 5, Part 2, starting with number 33. We have a book sliding across a level surface. Find the work done by friction. So we have the mass, 1.52 kilograms, the displacement, and the coefficient of friction. I draw a diagram to show that displacement and friction are 180 degrees apart from each other. So work done by friction is force of friction times displacement times cosine of 180. Force of friction, remember, is mu sub k times normal force on a level surface. Normal force is going to be the weight of the book. So mu sub k times m times g times displacement. Cosine of 180 is -1. So we get negative 2.59 joules. Number 35, a force given by the vector is applied to a cement block on a level floor. Find the work done if the block's displacement is, and there are three different parts to it. So work done, this is the easiest way to do it, to use this formula that's written here in green. Work equals the x component of force times the displacement in the x direction, plus the y component of force times displacement in the y direction. Apply this formula to each of them. So for part A, displacement is 2.5 meters in the x direction and 0. So we do multiplying the x components and then multiplying the y components. So we have 2.34 newtons times 2.50 meters plus, for the y component, 1.06 newtons times 0 meters. And that adds nothing to the work, the y component. So for part A, the answer is 5.85 joules. For part B, you do a similar thing. Now we're multiplying the x components, 2.34 newtons times negative 2.5 meters, plus 1.06 newtons times 0 meters, and we get negative 5.85 joules. For part C, 2.34 newtons times 2.5 meters plus 1.06 newtons times 2.5 meters, and we get 8.5 joules. Number 45, 13.4 joules of work compress a spring of 2.37 centimeters displacement. What is the spring constant? So work equals, let me just scoot this up here. Work equals 1/2 kx squared, so we're solving for k. K is 2 times work divided by displacement squared. Plug in those numbers. Remember, you need to, displacement, you have to do it in meters, so it's 0.0237 meters. And you should get 4.77 times 10 to the 4th newtons per meter. Number 47, the work done in extending a spring from 0.1 meters to 0.3 meters. So the work to go from a final position, from an initial position to a final position, is this equation here, 1/2 kxb squared minus 1/2 kxa squared. We can factor out the 1/2 k, and then we have 1/2 times 150 newtons per meter times the difference of the two squares, 0.3 meters squared minus 0.1 meters squared. And that gives an answer of 6 joules. Number 57, a boulder flies through the air. Given its speed and its kinetic energy, what's its mass? What would its kinetic energy be if its speed doubles or is cut in half? Okay, so start with kinetic energy is 1/2 mass times velocity squared. Solve for mass. 2 times kinetic energy divided by speed squared. And we get 3.97 kilograms. For part B, I've solved this without plugging in numbers till the very end, so follow this. Kinetic energy, I have K sub 2, so kinetic energy for the second part is 1/2 mv for the second part squared. Now, I replaced v sub 2 with 2 times v sub 1 because it's double what it was in part A. So it becomes 1/2 mass times 2v1 squared. This becomes 1/2 mass times 4 times v1 squared. When we move the 4 over to the side, we can see that this is 4 times the kinetic energy solved for in part A. Well, in part A, the kinetic energy was 305 joules. It's 4 times that because the speed was doubled. So we get 1220 joules. For part C, I've done the same thing, but I've replaced for the third velocity. Since it was cut in half from part A, it's 1/2 v sub 1. When you square what's in the parentheses, that 1/2 becomes a fourth, which we can slide out to the side, and we see that the new kinetic energy is 1/4 what the original kinetic energy was. So it's 1/4 times 305 joules, which is 76.25 joules. Number 67. A 25-gram bullet, so we'll convert that to 0.025 kilograms. At 310 meters per second, travels 15 centimeters into a tree before stopping. So we have a final velocity of 0 meters per second. What's the average force exerted to stop the bullet? Well, you could do this using kinematics. Solve for the acceleration and then use F equals ma. But let's use principles learned in Chapter 5. Work equals average force times delta x. Let's replace work. Let's use the kinetic or the work energy theorem. Work is change in kinetic energy. So change in kinetic energy equals average force times displacement. Divide both sides of the equation by displacement because we're solving for average force. The numerator, change in kinetic energy, that's final kinetic energy, which is 0, minus the original kinetic energy. So we get that the average force is negative 1/2 mv0 squared over delta x. Now the negative just has to do with what direction the force is in. It's opposite the direction that v0 was. In the end, we're going to give the answer as the magnitude of the force, not really caring to use the negative. So you should get 8,008 newtons. Number 74 asks, how far must you compress a spring in order to store so much energy? So here's the formula. Potential energy is 1/2 kx squared. Let's solve for x. X then becomes the square root of 2u divided by k, and you get 1.18 meters. Number 85, the roller coaster. Okay. You see my picture right here, state 1 and state 2 at the end. We start doing conservation of energy. E1 equals E2, excuse me, which becomes kinetic energy plus potential energy at state 1 equals kinetic plus potential at state 2. We're going to take the 0 of potential energy to be at state 1. So we'll consider that the ground level, 0 height. So we can just get rid of that. U sub 1 becomes 0. Plug in the values of each of these. So kinetic energy 1 becomes 1/2 mv1 squared. Kinetic energy 2 is 1/2 mv2 squared. Potential energy of 2 is mg times delta y. So delta y is how high it's gone above state 1. You notice that mass can divide out. I've, in this line, multiplied the entire equation by 2 just to get rid of the fractions. And we get that the final the velocity at 2 is the square root of v1 squared minus 2g delta y. So it's 11.4 meters per second. Number 86, a horizontal spring. A wad of putty is thrown horizontally at it at such a speed, and find the maximum spring compression. So you see my picture. E1 is while the wad of putty is flying through the air and the spring is at equilibrium. E2 is when it's finally come to full compression. It's gone as far as it's going to go. So I set up conservation of energy. E1 equals E2. So in the next line, I haven't written all this, but it's K1 plus U1 equals K2 plus U2. You realize that U1 is equal to 0. The spring is at equilibrium, so there's no spring potential energy. There's no gravity isn't involved here because everything's at the same height. So the only thing left on the left-hand side is kinetic energy 1. On the right-hand side, it's come to a stop, so the only energy is potential energy at 2. What this line means is that all the kinetic energy of the putty gets transformed into potential energy of the spring. So we plug in the values. 1/2 mv1 squared equals 1/2 kx squared. We want to be careful in doing this one that we use mks units, so 85 grams. You've got to make that 0.085 kilograms. We solve this equation for x, and we get x equals square root of mv1 squared divided by k. So we get 0.114 meters. Number 89, a rubber ball is dropped. What's the ball's speed when it hits the ground? You can use kinematics for that, but let's not. Let's use concepts learned in this chapter. Part B says it loses 25% of its mechanical energy. To what height does it rebound? Okay, so I've got 3 states here. State 1 is when it's high above the ground. State 2 is right when it's at the ground. State 3 is when it comes back up to its next maximum height. So we have E1 equals E2. There's no kinetic energy at 1. There's no potential energy at 2. So the energy for 1 is just U1. The energy at 2 is just K2. So we have mgy, and here y is the height above the ground. I'm setting the ground to be a height of 0. Equals 1/2 mv squared. And we solve for velocity. Square root of 2gy. And we get that the speed at the ground, or at state 2, is 6.86 meters per second. That's part A. Now, part B, it says that it loses 25% of its energy. So let's say it like this. The energy at 3 is equal to 75%, or 3/4 of the energy at 1. Now, in both states 1 and 3, there's no kinetic energy. It's all potential energy, so let's plug that in. For energy at 3, it's mg h sub 3, and it's at h sub 3 that we're solving for, equals 3/4 of E1, which is mg h sub 1. M and g divide out, and we're left with h3 equals 3/4 h1. So what we get from this is that if the ball only has 3/4 of its initial energy, it's only going to come up to 3/4 of its initial height. So 3/4 of 2.4 meters is 1.8 meters. What power to lift 350 kilograms from the ground to 23.8 meters high in 1 minute? Well, power equals work divided by time. Remember that the work done to lift something is its weight times its height. So mg times, or rather not its height, but how high you lifted it. This otherwise has been mg delta y divided by the time. So it's 350 kilograms times 9.8 newtons per kilogram times 23.8 meters divided by 60 seconds, and we get a power of 1,361 watts. And the last one, number 99. Find the work done by a motor, constant power of 8.5 kilowatts for 30 seconds. Okay, well, if in 98 you see power is work divided by time, then work is power times time. Power is 8,500 watts times 30 seconds, and we get a total work of 25,500 joules. And that's the end of chapter 5.